Hello, everybody. Welcome back. Thank you for joining us for another segment here of some application of probability and statistics to choice under uncertainty. To follow up with an earlier discussion we had started on the value of information. And to get things started, I'm just going to kind of roll through an example that we had set up prior. And this example involved uncertainty associated with oil drilling specifically. And we were considering the risk involved with drilling for oil in that a potential drill site can be either dry or wet, right? And this is determined by nature. And wet wells, obviously, they contain oil, while dry wells do not, and hence the latter are not as lucrative. And unfortunately, a well's state cannot be observed prior to committing to investing in a particular drill site. However, we have some past data from randomly drilling around that suggest that the unconditional likelihood of striking oil is about 20%, whereas the likelihood of striking a dry well is 4/5, is 80%. So the uncertainty that we face here, which is again fundamentally determined by really nature, is that the well can be either wet or dry for any chosen dig site. And, randomly digging suggests that we would strike oil 1/5 of the time and we would not hit oil 80% of the time, the remaining 4/5 of the time. And the cost of drilling, there's a cost to this. This is $5 million. And that cost has to be sunk regardless of whether or not the well is fruitful. And to simplify things here, we're going to assume that a wet well yields $35 million in oil revenue. You can think this is the discounted value of that well yield into perpetuity. And otherwise, the dry well yields a value of 0. So we can put those profit values at the end of the tree, right? Revenue minus cost in each situation. And now we can formalize a simple binary choice. And that choice was, given this uncertainty that we face ex ante, should we be investing in a drill site or not, given the unconditional likelihoods that we are privy to at this moment? So we have this decision node. We have this choice between investing or not investing. And if we chose not to invest, then we don't gain anything, but at the same point, we don't risk losing anything, and we get a certain payoff of 0. And we started kicking things off by asking, well, without any additional information, what is the optimal action here if we're an expected monetary payoff maximizer? And to answer that question, this required that we compute the expected payoff resulting from either choice at our decision node, and not choosing to invest has a payoff of 0. So that's the easy case. So let's go ahead and compute the expected payoff resulting from an investment decision. And we can compare that to 0, right? So if we do take that weighted average, that 1/5, 4/5 weighted average of 30 million and minus 5 million here, then we find that on average, right, we would be making 2 million from investing, given this uncertainty of the state of nature, which we can't observe ex ante. So that being said, the choice I think is obvious. We would want to invest because otherwise choosing not to yields a 0 payoff for us here. So the optimal decision here is to invest in that drill site, which yielded us an expected payoff of $2 million. And that's going to be an important value that we're going to have to reference later, that $2 million figure here. And what we want to think about now is the opportunity to drill, but after observing a signal, okay, a report from our geologist, right? Geologist is going to tell us how good is that drill site, what's in the ground. And I know in previous segments we had solved this problem for geologists of varying precisions, but what we're going to do today is we're going to incorporate our geologist into the picture here, where the geologist can again run this test before we have to commit to making that investment decision. And the results of this test, again, provide us this observable binary signal realization where we're either getting a good report indicative of a high likelihood of oil in the well, or a bad report indicative of probably a lower likelihood that there is oil in the well, and it's likely to be a dry well. And the goal here is to think about valuing the geologist's report. We want to value the signal across both potential realizations. And for each realization, right, he could give us a good report. We're going to face that same decision, should we invest or not. And we also face that in the event he tells us that things are not looking good. So the full scope of our decision tree now gets a little bit broader, where that gray node was the signal realization. We had still now decision nodes, but we had two of them, one for each possible signal realization. And we had our state of nature being chosen at the ends of the tree, again, for both possible realizations of the signal. And our goal, again, is to compute the value of the geologist's signal. Okay, we want to compute the value of the information. And the three-step approach we've been taking, right, involves us first figuring out what is the payoff to a rational individual without the information, which we just looked at. That was $2 million, and we'll revisit that. And this, again, is assuming that they are behaving optimally ex ante. And the next thing we're going to have to do is, in that larger decision tree, we're going to have to compute what is the expected payoff using the information. And again, assuming optimal decisions are being made for every possible realization of that signal. And then last but not least, once we compute those two profit values and expectation, we'll be able to compute the value of information by comparing them and seeing how much that information has increased profit when it is used optimally relative to not having it. So we've looked at cases of very specific numerical values of precision. We looked at perfect signals in the past. We looked at imperfect signals where the precision was maybe like 50%. What we're going to do today is we're going to look at a general signal where instead of the precision having a particular numerical value, we're just going to assign it this value P. And what we mean by general is that we're going to treat P kind of like a variable in the problem and carry it around with us so that we can see at the end of the day, how does P, this precision, affect the value of the signal itself? So we'll be able to relate signal quality to signal value, right? The quality of the information to the value of the information at the end of the segment. And to keep things simple, we're going to assume here that the precision, right, or the report rather, is equally precise regardless of the state that we are conditioning on. So regardless if it's a wet well or if it's a dry well, we're going to assume here that we are equally skilled. Our geologist is equally skilled at identifying either of those. He's equally precise. And again, if you don't remember your terminology here, whenever we are conditioning on the state, right, probability of the signal given the state, that is precision. However, that is not the same as the forecast accuracies. And forecast accuracies, we know from prior segments, are related to these events at the tail end of the trees, which do not condition on the state realizations, but they condition on the signal, right? Given good or given bad. Okay, so precisions condition on the state, but forecast accuracies condition on the signal realizations. And we have to use Bayes' rule to figure out the conditional probabilities given those signal realizations, given a good outcome or given a bad outcome, right, in terms of the report provided by the geologist. And this is a good time if you want to stop and pause the video and use the information given to calculate these probabilities using Bayes' rule. You can do that right now. Okay, but I will show you the next step in that calculation. So you could pause it now if you want to substitute the values given. Okay, and if you wind up doing that, okay, you should see things substitute nicely, and we wind up getting not super convenient values. They're fractions. They have variables in both the numerator and the denominator. Okay, but the math is manageable here. Okay, it's manageable, and things will cancel out in a nice way at the end. So if you think the numbers are going to get crazy, they are manageable. All right. Now, those forecast accuracies, those are the probabilities that go at the ends of the tree, given a particular signal realization, right? We're conditioning not on the state, but we're conditioning on the signal realizations, good or bad here. So after, for example, good or bad take place, then we face those particular probabilities, right? We face the forecast accuracies or our posterior beliefs of whether or not the well has oil in it or it's empty, right? After a good report, or we have slightly different posterior beliefs following a bad report. Now, the other probabilities we should be able to compute at this point are related to the likelihood of observing good or bad signals. And hopefully you remember that looking at that Bayes rule calculation, the probability of good and bad are actually buried down in the denominators, right? That's the probability of the good signal. And this is the probability of the bad signal in the denominator below in that bottom expression there. So what we should be able to do here is just use those expressions in blue in the denominator, and we can simplify them and replace them at that signal realization node, reflecting the likelihood of observing either a good or a bad signal from the geologist. Now, given all of this, we can begin computing expected payoffs conditional on signal realizations. Okay. And the idea is we want to characterize what is the optimal action for every possible signal realization. And here we have two, right? It can either be good or bad, right? It's a binary signal. So to do this, we're going to compute the expected payoff resulting from the optimal actions for every possible signal realization, starting at the ends of the tree and using some backwards induction to work ourselves back to the beginning node. That is the signal realization node where we will be able to calculate the value of that signal, regardless of the realization, right? Accounting for the likelihood of either realization. This time, though, things are going to be a little bit different in that our optimal decision rule will actually depend on the value of P. It will depend on the quality of the information that we are given. And we're going to have to work our way backwards and apply that three-step process. We already did step one a moment ago. We figured out the value without a signal. If we just drilled randomly, would be about 2 million if we took the optimal action of drilling, right, versus not. But we're going to need to work our way backwards to follow step two and figure out, well, what is the expected payoff when we use that information optimally? And now we are able to be in a position to answer that question. So let's think about the conditional expectation of the profit resulting from an investment following a good signal realization, which means we're going to be in the top half of this tree diagram along that yellow path there. And what we're going to be looking at is computing the expected payoff that results from that particular realization of nature's choice. And if we weight the 30 million and the minus 5 million by the associated probabilities in those branches, and we're careful with our algebra, we can wind up with an expression for our average profit if we were to invest, right, following a good signal. And as long as this number, right, as long as this number here is bigger than 0, then the optimal action will be to invest, right? Because 0 is what we get from non-investing. And if you set that expression greater than or equal to 0, if you were to do that, then you find a condition on P that defines how precise the signal needs to be for you to invest after your geologist tells you he thinks things are good, right? So this is essentially saying, how good is good enough for me to listen to my geologist after he gives me a good report? And the answer to that question we can see here after setting up this inequality is that following a good signal, investing is only optimal provided the geologist's precision is at least 40%, at least 2/5. Okay, so as long as he's at least that good, we'll listen to him after a good signal and we will invest. However, what about after a bad signal realization? Okay, if we're on the bottom half of that tree, right, follow that yellow arrow, we observe a bad signal realization. Now we need to compute the expected payoff in this blue circular region at the bottom right of the screen here. So again, we're taking that weighted average of 30 and -5 here, 30 million and -5 million, right, weighted by those two forecast accuracies. And again, with a little bit of algebra, you can simplify that down to 30 minus 50p, all divided by the quantity 1 plus 3p. And again, as long as that quantity is positive, right, or at least 0, non-negative, then investing is going to be an optimal decision for us. Okay. Now, if you set up the inequality to make this expression greater than or equal to 0, you wind up getting kind of a weird condition. And the condition is that you will decide not to listen to your geologist, right? He gives you a bad signal here, but we're still investing. We're not listening to him because his precision is sufficiently bad. It's small enough. It's low enough. How bad is bad here? Well, following a bad signal, if his precision is lower than 60%, lower than 3/5, I'm not going to listen to him and we're going to invest anyway. Okay. However, if P is bigger than 3/5, right? If he's more precise than 60%, then the optimal action would be to listen to him and follow his advice and to stay out and not invest, but not if P is low enough. If the precision is low, if our expert geologist is not that good of an expert, then we may opt to not listen to his advice. And that's what's actually happening here if you take that bottom green route following the bad signal realization. Okay, so to summarize, right, we had this expected payoff of 50p minus 20 all over 4 minus 3p, and that was following a good signal, given that we invested, and this was only optimal if the geologist was sufficiently good enough, right? If he's good enough, we'll listen to him when he tells us things are good and we drill, but only if his precision is at least 40%. He's got to be at least 40% accurate for us to listen. Or sorry, 40% precise. Okay. Following a bad signal, which yielded an investing average payoff of 30 minus 50p all over 1 plus 3p, right? Investing was only optimal, and this was us not following the advice, right? He said bad, but we still invest only if the precision is low enough, if the expert is bad enough. How bad is bad? If it's lower than 60% precise, then we're not going to listen to him following a bad report, and we would invest anyway. Okay. So at this point, you should notice that we've kind of divided up the region of P, right, the precision, I would argue, into 3 cases. And if you look at the P axis here, where you can kind of think about, right, P is the precision, it's between 0 and 1, right? Closer to 0 is lower signal quality, closer to 1 is higher signal quality. We can break this down into 3 regions here. Okay, there's a region where the signal quality is what I'm going to call sufficiently low. And when we're in that region, okay, the optimal actions involved us not listening to our geologist. We didn't listen. We would do the opposite, right? If P is lower than 2/5, okay, then we do not invest when he tells us we should. Okay, why don't we? Well, the geologist is not very good. His precision is very low. And if it's very low, we don't listen to him. Okay, if he tells us it's bad, then we do the opposite. We invest if the signal quality is low. Okay, however, if the signal quality is intermediate, okay, that means it's good enough for us to listen to his advice, right, after a good signal, but we also do the same thing after a bad signal, and we don't follow the advice after a bad signal in this region, okay, which means we're investing no matter what. And you might recall that our optimal actions, investing no matter what in this region here, that's exactly what we did in the absence of the information. And this is what we would do with the information for both realizations. And that should immediately give you an idea of what the value of the information has to be if the precision is in this range here. Okay, it doesn't cause my actions to change relative to what I would have done without the information. And that's true for every possible signal realization. If he tells me it's good, I invest. If he tells me it's bad, I invest. What would I have done without the geologist? I would have invested. Okay, so if you're wondering, oh, does that mean the information is not valuable in that region? I'm going to suggest yes, and we'll come back to that. You will see that. Now, what if the signal quality is sufficiently high? It's in this region where it's at least 3/5. Well, if it's at least 3/5, then it's also at least 2/5, meaning we're satisfying that condition, but we're not satisfying this condition. Okay, so if we're in that region, what that means is we're going to listen to our expert regardless of what signal he gives us. We listen to him. And we invest following a good signal, and we stay out following a bad signal. And so what we're going to have to do here is compute the value of information in each of these three intervals for each of these three cases, so we can see how the value changes with the precision within these regions. Right? We're going to see this picture again in just a moment. So here is where we were. And we want to simplify the tree here at this point, right? We can start putting those expected payoffs after investing at the ends of the tree. Okay, and we can recognize that, following those green paths were the optimal decisions. And we can now see those were only optimal for certain values of the signal quality, for certain values of the precision. If P was greater than or equal to 2/5, investing was optimal. However, if it was less than or equal to 2/5, then we did not satisfy this condition on the left. So in that case, then investing would not be optimal, and we would take that different green path. Okay. So whether or not we're taking an optimal action in a given decision node depends on the quality of the signal. Okay. Similarly, at that bottom decision node, right, we're only investing if P is less than or equal to 3/5. If the signal is sufficiently poor, then we don't listen. However, if this condition is not met, then the optimal action is to listen and to stay out after a bad signal, provided it's sufficiently large. Now, you might be looking here and saying, hey, it's kind of weird, right? Greater than or equal to 3/5, less than or equal to 3/5. What happens if P's equal to 3/5? And the answer is both actions would be optimal because they yield you the same maximal expected payoff. And that is why it's possible to have less than or equal and greater than or equal here, if you're wondering about that. Now, that being said, okay, we should be able to kind of go through our three cases here and think about what is the expected profit in every case of quality ranges we could fall into. For example, case one involved very low signal quality, right? And the optimal actions, involved not investing after a good signal and investing after a bad signal. So in this case, right, we were not listening to our expert, right? Weren't listening to him. We did not invest after he says good. He gave us the go ahead. And we do invest when he says bad. So we're doing the opposite of what he tells us here. And when we do that, we can weight the expected payoffs in green at the end of the trees by the likelihoods of observing either signal realization. And that allows us to compute the expected profitability with the information here. Okay, so we can fill in those blue values for the probabilities of good and bad. And that calculation is not terrible to go through. You'll notice, right, the 1 plus 3p cancels. This whole term cancels to 0 here. So you wind up with 6 minus 10p, where again, p can only take on the values between 0 and 2/5. So you can't plug a 1 all the way up here if you're wondering, oh, can p be 1? Can that be negative? Answer is no. In fact, the lowest it can be corresponds to plugging in the highest value of p into that interval, which is 2/5. And you should see that if you plug in 2/5 for p, that drives that expected value down to a familiar place. I'll come back to that. Now, what about case two? And well, case two, we had kind of an intermediate quality signal here. And by intermediate quality, I mean, it wasn't really informative in that it didn't change our actions relative to what we would have done without that signal. So in case two, when P was in this region, right, we were investing no matter what. Our optimal actions were exactly the same as what we did without the information. So what we should find here is that if the information quality is in that region, right, if the precision's between 40% and 60% of it's not that good, okay, then if it doesn't change our optimal actions, we're going to see it's not going to improve our expected profit outcome. And if we were to do that same calculation now, but considering us investing regardless of the signal realizations, the calculation's a little bit more complex, but again, you'll notice you get things canceling right away. Okay, and then you can add the terms together, and you'll notice the P's actually cancel out. And you get an expected profit with the information of 2 million. And if you're thinking to yourself, well, hey, that was the exact same expected profit we got from drilling without the information, you would be exactly right. So we can revisit that picture we saw a moment ago at the beginning of this segment and recall that the optimal action without information, right, without that signal, okay, was to invest, right? We got 2 million. We didn't, we got 0. So we would always choose to invest without information. So in case two here, looks like we were investing after a good signal. We invested after a bad signal. That's what we would have done anyway without the information. And it shouldn't be no surprise that when you do that, run around just drilling randomly, even with the geologist telling you good or bad, you disregard bad and you still drill, that you're going to make the same expected profit as you would have without him. Now, what about the last case? Well, the last case, case 3, involved sufficiently high signal precision, right? And in this situation, we recognize that our optimal action, conditional on either signal realization, was consistent with us listening to the geologist. When he says it's good, we invested. And when he says it's bad, we listen, we stay out, we don't invest. And again, we can calculate the expected payoff resulting from that particular choice of optimal actions in case 3 here for high signal quality. And when you do that, again, you get some things that cancel fairly nicely. We saw that 4 minus 3p canceled in the last calculation, actually. The second term cancels to 0 because you are staying out after a bad signal, which pushes the expected payoff with the information to 10p minus 4. And again, the lowest you can make p is 3/5 here. The highest it can be is 1. And if you think about, well, what do we get when we plug a 1 in there that actually corresponds to something that we've talked about already? I'll come back to that. Okay. But at this point, I think it's useful to summarize what we've kind of stumbled upon here, right? We have these 3 different cases. And in each of those cases, right, regardless if we were in a, low quality information setting, if we were in a medium quality of information setting, or if we were in a high quality of information setting, we were able to compute the expected profit values that result from optimally reacting to that information, right, for any given signal realization. Now, we know from earlier, because we worked through this example in past segments and we ran through it again right at the beginning of this one, that without any information, right, without that geologist, we would still choose to drill at random and we would be raking in $2 million in expected profit. So all we need to do to figure out the value of the information is to take these values in blue and we're going to subtract out the expected profit that we get without using the information, and that'll give us the gain. So the value of the geologist signal, okay, which again depends on P, the precision, looks just like the values on the left, with the exception that we've subtracted the 2 million, right, from each of those values. So 10p minus 4 becomes 10p minus 6, 2 becomes 0, 6 minus 10p becomes 4 minus 10p. If you're also wondering, well, didn't we take a max between that and 0 before? We did, but you should be able to just verify yourself that each one of these values for the range of the probabilities that they're associated with cannot be negative, will not happen. And so implicitly, we've already taken that maximum over the payoffs, right? The maximum over those payoffs difference and 0, it's not shown here, right? But we've done that check, and you should always verify that that is the case, right? The information can never make you worse off. If it does, you just disregard it. So we have this value function now, and you'll notice it has some, I think, interesting properties, right? If we were to graph it, okay, we could think about graphing it, for any value of signal quality here, right? We could be low value in that red region, intermediate in the gray, or high value in the green, high quality in the green. So what we're going to do here is we're going to plot the value of information on the vertical axis against the quality of it. Okay. And when we do this, you'll notice we're going to wind up getting a piecewise linear function. Okay. And the first case we'll look at here is, well, when we're in the low signal quality region here, right, that means the precision is between 0 and 40%. Okay, the optimal actions here involve us doing the opposite of the advice given to us by the geologist. We did not invest following a good report, and we drilled following a bad report. And it might surprise you that the information is valuable in this region. In fact, it actually turns out to be extremely valuable in this region. Okay, and that's because the expert is so bad that they're actually good. Like if the weatherman's always wrong and he tells you today it's not going to rain, If you know he's always wrong, probably you're going to bring your umbrella to work, right? And that's kind of what's going on here. And I'm going to come back to that idea in just a moment. So in that region, we can plot 4 minus 10p, right? It's got a vertical intercept up at 4 when p is 0. Okay, that is the value function in the region, right, where we had low signal quality. We can think about, well, what happens if we have intermediate signal quality, if the precision is between 40% and 60%? And if we're in that range, right, then our optimal action, we recognized, did not change relative to what we would have done without the information, right? We invested after both signal realizations. And that being said, right, we suggested before, well, if our optimal actions don't change relative to not having the information, then it can't be valuable. And that's exactly what we're seeing here, is that when the precision is between 40% and 60%, the information is not valuable. It's not precise enough to be informative to the point where we would take a different action than we would have taken in the absence of that signal. Last but not least, case 3 was our high signal quality situation. So our precision was at least 60% in this case. And when the precision was at least 60%, our optimal actions involved listening to the advice of our geologist in both situations, after a good signal and after a bad signal. Okay, we invested after good, we stayed out after bad. And when we did that, our payoff was 10p minus 6. And if you graph that over here, and that looks like the following. And what we have now constructed here is the value function. This is how the value of information depends on p, which is a measure of the quality of that binary signal, right? And in this case, it was symmetric, right? We said equal quality in identifying both a wet well and a dry well, right? And that was p. So it was a symmetric signal in this particular case. But nevertheless, we're able to see, I think, a pretty interesting result here that I believe is probably somewhat counterintuitive to what you might have thought about how, improvements in the quality of something might translate into the value of that something. So we've constructed this value function as a function of p, and we should be able to verify a few of the important cases that we've seen in prior segments. For example, if we were to plug in a value of p equals 1, that corresponds to a perfect signal. That's when the geologist gets it right every time. And if you plug a 1 into the value function, right, then it's got to go in over here. You get 10 minus 6, which gives you 4, which you'll notice is the maximum value of information. That was the value that we had gotten in a prior segment when we valued a perfect signal. It was 4 million. We also looked at a case where, again, it was symmetric, but it was basically a coin toss. Our geologist was running around flipping a coin, telling us good or bad. And when he did that, we kind of realized, well, it's a coin toss. And it's as if he's not even looking at nature. I knew there was a 20% chance of striking oil and an 80% chance of not randomly. So if he's just flipping coins, I'm not even going to listen to him. His information's not really valuable. And that is exactly what we had found in a previous segment, that the value, if you plug in 1/2 into the value function in the proper interval, comes out to 0. Okay, now something that might surprise you here, it surprised me the first time I saw it, is that when the precision is at 0, when the geologist is never correct, it might surprise you that this yields the maximal value just like a perfect signal does. And the reason this happens is because even though the signal quality is terrible, it's in fact so bad that it winds up actually being perfectly informative despite being incorrect, right? If the weatherman's always incorrect and tells you, hey, it's going to rain today, then oh, it's not. And if he says not going to rain, then you know, oh, it is. And you adjust your optimal actions accordingly. So in that regard, the signal is reliably always wrong. And because of that, at low qualities, it actually has a lot of value. Okay. So I would like to wrap up this segment by discussing an important feature of this value function, and that is the non-monotonicity of the information value. Usually we use this term monotonicity to refer to a relationship that is either continuously, increasing or decreasing, globally. And you'll notice that as the precision increases, right, the value of the information doesn't just increase with improved signal quality. Okay. And, I think your intuition suggests that probably as the quality of something goes up, its value will go up as well. But the intuition is misleading, I think, in this case, because the value of information relies much more on just the precision. It relies on whether or not the marginal improvements, in the information quality have caused actions to change in a way that improves the profit outcome. And as we've seen already, if the actions do not change in response to improved information quality, then the marginal improvement in information quality is not going to add any value. Okay, now, where does that happen? Well, you can see that happens in this red region here, right? That red region is exactly a situation where we can move a little bit to the right or to the left in that region. We can change the quality of the signal, but a small improvement will not improve the information value. For example, if the precision went from 50 to 55%, it doesn't quite reach the threshold of 3/5 at 60%, and we would not get an improvement in the value of that signal despite the fact its quality is improved. Okay. Now, there is also a region here that we identified before where improvements in signal quality do something strange, right? Counterintuitive, and that is they reduce the value of information. That happens in this red region that is flashing on the left portion, right, for case 1. And in that region, right, the signal precision actually decreases the value function when the precision increases. And that's because the signal quality was already so bad that it was reliably informative. So a small improvement in the quality means that the quality starts approaching the intermediate quality range where it no longer becomes pivotally informative, despite the fact that it is more precise. Last but not least, in case 3, we were dealing with sufficiently high quality, and if we were in this region and only in this region, is there an increasing monotonic relationship between the quality of the information and the value of the information? Okay, only in that region do increases in signal precision actually translate to increases in the value function. All right, so a few concluding remarks to wrap up this segment here where we looked at a general signal, right, with general quality defined by the precision P. And in terms of concluding remarks here, right, despite what intuition and instincts might suggest, there is not a strictly increasing relationship between information quality and information value. Information quality is only valuable at the margin if it results in some change in actions yielding a higher payoff and expectation from that information. And it's entirely possible that marginal improvements in information quality are not pivotal enough to cause actions to change, and hence are not valuable in the sense that we've discussed herein. Now, moving forward, why is this important? Well, I would suggest that understanding these facts are critically important when we want to consider trade-offs faced when producing information goods, right? This is the value of the precision, but we haven't really thought about the cost of that precision. Okay, so if there's some cost of getting precision P, and we have to trade off the value against that cost, right? We want to think about, well, what conditions characterize the optimal quantity of information production? And we're going to move into that idea a little bit later. So hope you enjoyed that. That'll wrap up this intermediate segment here on the value of information with our oil drilling example. So this is another good application here of our probability and statistics applied to choice under uncertainty. And take care. I will see you shortly in the future.